Okay, so let's continue. Let's use our classroom temperature example to further illustrate the concept of normal distribution. Again, let X be our room temperature when the next lecture starts. Okay, we know it's not uniform, and in the previous videos we used a level function to describe its randomness. We say, okay, within 20 to 30 we have one single number for the PDF, and so on and so on. There we say, basically, within 20 and 30, this random variable is uniform because the probability is the same. But now let's use a different way to do it. Let's assume that X is a normal random variable with mean 25 and a standard deviation 5. So in other words, we are having a different random variable. Okay? This X is different from that X because their distributions are different. In practice, you need to collect some past data and do some estimation about the distribution. Okay? If you see it's more like the previous one, then you probably would say, oh, okay, so the distribution is like that. Or if you see something like the example here, then we're going to say, oh, okay, my distribution looks like a normal distribution with this standard deviation with that mean. Okay, let's assume we have done so. And let's assume here, we know that X is normal with mean 25 and the standard deviation 5. So if we depict the PDF, it would be something like this. Okay, you see a bell-shaped curve, the first thing. The second thing, the mean is at 25. The mean is at 25. The probability for you to see some values close to the mean is high. Extreme values have small probabilities. Okay, that's normal distribution. The absolute values of your PDF are not important. What importance are the probabilities for X to be within a region? Okay, that's CDF. That's CDF. As an example, suppose the lecture would be cancelled if X is too small or too large. Okay, we cannot have lectures in a very hot or very cold room. So let's assume we have the rule imposed by, by me. And then the probability for the lecture to be cancelled would be an important message to you, right? If you predict that the lecture would be cancelled, then you would not like to come to the school. Okay, so that's an important thing to you. So you want to calculate the probability for X to be less than 15 or greater than 35. You know that this is a collection of two events. So when you want to calculate the union probability, it's just the sum of these two probabilities. Okay, so you calculate the probability of this and the probability of that and sum them up. Interestingly, you can see that according to the curve, if you depict the two regions, okay, from 0 to 15 and from 35 to, for example, 50, you can see that because the curve is symmetric, so these two probabilities would be the same. Okay, these two probabilities would be the same. Or technically, because the mean is 25, right? And the difference between 15 and 25 and the difference between 25 to 35 are the same. So that's why, according to the symmetry of the curve, you can see that this part and that part, the two shaded areas, they are exactly the same and they have the same area. Okay, so that's why you have this equality. And that's why this probability and that probability are the same. Graphically, it's here and here. We want to find the probability for x to be small and large. That means we want to find the area of the shaded region. Okay? Eventually, we can do the calculation, and as you can see, the probability is not high, and that specific value is about 5%. We will tell you how to do that in class, and here, all you need to know is the concept. When you want to calculate a probability, you need to know where it is. Okay, it's here and here. There's one specific thing called standard normal distributions. Okay, it's simply the normal distribution with mean 0 and the standard deviation 1. Now, when these two numbers changes, your curve will shift to the left or right. Your curve will become flatter or not. Okay, so when we fix the two numbers to be 0 and 1, we have something special called standard normal distributions. Standard normal distribution is very interesting thing, because in fact, all the normal distributions are equivalent, because you can transform this to that to another one, and all the normal distributions can actually be transformed to the standard one. Technically, if x is a normal distribution with mean mu and a sigma, x is a random variable, then you plug in x to a standardization function. For any realization of x, you subtract mu from it and divide the outcome with sigma. Once you do this, you're going to get another value, right? And then that random variable would follow the standard normal distribution, which look like this. The mean is at the mean is at 0 with a specific standard deviation. That transformation is called standardization. We won't say that standard normal is required for all the tasks that you're going to do. But one most important thing is that all the normal distributions, they are somewhat equivalent, because you can scale them. You can make them larger, smaller, whatever, and the transformation allows you to connect all the normal distributions. Okay, we're going to see why that's important. So anyway, let's continue. So consider a set of data. Recall that we defined something called ZScore to you. Okay, given any value x, we can use this formula x minus mu divided by sigma to define z, the z-score for that specific value. And it measures how far the value is from the mean using the standard deviation as the unit of measurements. Just like if z is 2, for example, then that value is 2 standard deviations above the mean. If z is -3, then the value is 3 standard deviations below the mean. Now that's z value. Then let's ask the question, well, is 2 sigmas away from the mean normal or not? Is that considered normal, typical, or not? To answer this question, basically we want to calculate the probabilities in some sense for that to happen, or the probabilities for even more extreme situations to happen. Okay, we want to ask, what's the probability for your x to be far from your mean by more than 2 standard deviations? Okay, in general you can do it, but before that, let's consider our temperature example. We know our x is a normal distribution, random variable with mean 25 and standard deviation 5. And we calculated this probability. The probability for x to be less than 15 and greater than 35. You can see immediately that 15 is 25 minus 10, and 10 is 2 standard deviations. 35 is 25 plus 10, and 10 is 2 standard deviations. So this probability exactly tells us for this normal distribution what's the probability for your value, for your x, to be far from your mean by at least 2 standard deviations, and that's just 5%. Okay, that's just 5%. And this can be generalized because all the normal distribution curves can be scaled. So for a normally distributed random variable, it will have the chance to be so far from its expected value. Okay, extreme values are always possible, but to be 2 sigmas away from your mean, you only have probability 5%. Okay, and recall our 3 sigma rule for detecting outliers. You can do the calculation and find this probability. That's the probability for a normal random variable to be 3 sigmas away from the mean. That's just less than 1%. The probability is just 0.25%, okay, roughly. So that's why the distance of 3 sigmas is suggested, because suppose your data set, suppose that variable follows a normal distribution, then it's so unlikely for a value to be 3 sigmas away from the mean. Okay? And if that happens, you should take a look at it to see whether there is something wrong or it's just so extreme. Okay? But you should look at it. So now we have some kind of justification for that. 3 sigma is likely to happen. That's why you should look at it. Okay? So in practice, if we are talking about, for example, production or manufacturing, there is something called quality control and a rule called 6 sigma. 6 sigma. And you probably have learned it in operations management, or if you haven't, then you will do that in the future. But anyway, as long as the distribution is normal, we have the following properties. The probability for a value to be within 1 sigma from the mean is 68%. Okay? 68% is the probability of this region. Okay? Within 1 sigma, the probability is 68%. Within 2 sigma, okay, from here to here, within 2 sigma, the probability is 95%. Within 3 sigma, it's almost 100%, and within 6 sigma, it's almost 1. It's almost 1. So when we do quality control by imposing this 6 sigma standard, that means we want our products, the products we manufacture, are all within the quality standard with this probability. Okay, we want almost all our products to satisfy our standard. So that means we are very strict in imposing that standard. Okay, so that's the idea of 6 sigma. We want a very high yield rate for our products. Okay, obviously the calculation of these probabilities depends on using the CDF. Because you are calculating areas below the PDF curve. Okay, we're going to tell you how to do that. Basically, we call some functions, call some Excel functions, for example. Okay, we will tell you how to do that in class. But the most important thing still is the concept. You need to know for which region you want to calculate the probability. Okay, because you are the one who will call the function. You need to know for which region you want to calculate the probability. And then you call the function, they will do the calculation for you. Okay, so that's the end of today's lecture. Thank you.